We have talked about 4 methods of loop detection in a linked list. Here we are going to talk about a method that does not modify the structure, does not modify the list, does not take big O of n auxiliary space, works in big O of n time. So that is why it's really popular method. We'll see how does it work, we'll discuss its implementation, and then we'll talk about mathematics behind it. How does it work mathematically? So the idea of this method is this. We begin 2 pointers from head, slow pointer and fast pointer. We move both of them ahead, and this is how we move. We move the slow pointer 1 position at a time and fast pointer 2 positions at a time. And we claim that if there is a loop, then they'll definitely meet at certain point. And if there is no loop, then they'll not meet. You will end up having null at the end, right? You will end up reaching null. So what do we mean by moving by 1 and moving by 2? So slow and fast are initially here. After one movement, slow will come here and fast will come here. Both were initially here. Slow moved 1 and fast moved 2. After next iteration, slow will come here and fast was here, it will come here. After next iteration, what will happen? Slow will come here and fast will come here, right? Because slow is moving 1 at a time and fast is moving 2 at a time. So fast came from here to here. Now what will happen after the next iteration? Slow will come here and fast will also come here. So they'll meet at this point, and that is how we detect the loop. Because they met, so we say there is a loop. They met at this point, so we say there's a loop in the linked list. Now let us talk about implementation and working of this algorithm. Let us now talk about implementation of Floyd algorithm for cycle detection. So we just discussed this approach. We begin slow pointer from here and fast pointer also from here, right? If we are programming in Java or Python, then we say slow reference and fast reference. And this is what I've done in this code, right? I begin slow and fast from the head of the linked list. Now what I'm doing, I am running a loop where I am moving slow 1 and fast 2. Fast equal to fast arrow next, right? And if they meet, I return true. Now there are some important points to note in this code. We have fast p not equal to null and fast p next not equal to null. These conditions are very much required. If I miss this condition, then I'll have null pointer exception for certain cases. For example, if I have a linked list, what will happen here? Your fast is initially here, your fast comes here. Now fast is not null, so you will do fast, you will come inside the loop. Suppose you do not have this condition, and you will access fast arrow next, and fast arrow next is null arrow next, which will cause null pointer exception or runtime error, right? So that is why we need to have this condition, because our input linked list might be a linked list that does not contain the loop, because we need to figure out whether there is a loop or not. So to handle normal linked list, we need to put this condition, because we are moving fast 2 positions ahead. Now one more interesting thing, why are we putting this condition after moving the pointers? Why not at the top? The answer is this: if you put this condition at the top, then this code will return true for every linked list. What will happen? For every linked list, you will have slow equal to head and fast equal to head. Both are initially head. You will come inside the loop. Say your linked list has certain nodes, right? You will come inside the loop, and then slow and fast are equal, right? Because initially they are both head. So it will return true for a linked list which do not even contain the loop, right? Any linked list which has one or more nodes, right? So say this linked list, what will happen? Fast and slow initially are here, right? Fast and slow both are here. And then we come inside the loop because fast arrow next is not null, fast is not null, and fast arrow next is also not null. We come inside the loop and say this condition is at the top, then what will happen? They both are pointing to the same node, we'll return true, even if there is no loop. So we need to put this condition after moving the pointer. This is an important point to note in the code. After we come out of the loop, you may come out of the loop due to the reasons that either fast p became null or its next became null. In any of these two cases, your linked list does not contain loop. So you will return false in this case. When you come out of the loop, you will return false. Let us now see how does this code work mathematically. How is this algorithm working all the time? So the proof of this algorithm, the working of this algorithm is based on these lines. First thing is your fast pointer will always enter into the loop before or at the same time as slow pointer, right? So if your whole linked list is a loop, then they will both definitely reach at the same time, slow and fast. But if your linked list is like this, then your fast pointer is going to reach inside the loop first. So when fast pointer is already inside the loop, when slow pointer is about to enter inside the loop. So when slow pointer is here, fast pointer must have been here, where k is greater than or equal to 0, right? That's what I've written in the second point, right? So there must be some distance k where k is greater than or equal to 0. Now the next point I've written here is the distance between slow pointer and fast pointer keeps on increasing by 1, right? So what do I mean by this? Say slow pointer is here and fast pointer is here. What will happen in the next iteration? Slow pointer will come here and fast pointer will go to the next of next. Fast will come here. So the distance that was k from here to here, distance will be k plus 1, right? This distance was k, this distance will be k plus 1 because this has increased by 1 but this has increased by 2, right? So the distance between these two pointers now become k plus 1. And what will be the distance after the next movement? It will be k plus 2. And next movement k plus 3. So the distance between two pointers keeps on increasing by 1. Here distance, I mean number of edges, right? So when I say my linked list is like this, right? And fast is here, say, then the distance between these two is 2, right? This is the distance. Now if it is increasing by 1 all the time, then there will be a point when distance will become equal to number of edges in the whole cycle or cycle length. Say n is the cycle length, so this distance will become n, and what will happen when the distance becomes n? They will be at the same node, right? So if you are in a cycle and cycle length is n, and if the distance between you and other person is n, then you are at the same node because you're looking at the distance from the other perspective. If you see in the other direction, then the distance will be 0, right? So the idea is this: since you are moving one pointer twice and one pointer at the half speed, what will happen? The distance will keep on increasing by 1, and there will be a point when distance will become equal to cycle length, and when that happens, they are at the same node. That is why we say that if there is a loop, then they meet at some node. Now the question arises, why not 3 times? Why not 4 times? Why twice the distance? See, if you are increasing a value k by 1 and you want it to reach n always, right? Then you can only ensure that it will reach n only when you increment it by 1. If you increment it by 2, what will happen? It will reach n minus 1 and then n plus 1. We might not reach n all the time, right? So that is why we pick the speed as twice, so that the distance keeps on increasing by 1. It is initially k, so k will definitely become n. So say k is 3 and n is 7, so k will become 4, 5, 6 and then 7, right? So when you are increasing 1 by 1, they'll definitely meet. Let us do a dry run of this algorithm to understand it better. Say slow is here and fast is here, right? What do? We move slow here in the first iteration and we move fast here. In the next iteration, slow comes here and fast comes here, right? Now your k is 2. The distance between these two is 2 right now, and we see that the distance is going to increase by 1 in every iteration. So this is the point I was talking about. Slow is about to enter into the loop and fast is already k distance ahead. Now what will happen? Slow will come here and fast will come here. What is the distance now? 1, 2, 3. So k is 3 now. Your k is 3. And what is the length of this loop? What is n? 1, 2, 3, 4. So they will meet next time because k will become 4 next time. Let's see what happens in the next iteration. Slow will come here and fast will also come here. So slow comes here and fast also comes here, right? Because fast was here, it jumped twice, so it will come here, slow will come here. Now what is the distance? K is n, right? So when k becomes n, the length of the loop, which is 4, then they will meet, because n means the distance becomes now 0. They are at the same point. So that's the idea. That's the dry run of Floyd's algorithm. Let's now quickly understand the time complexity of this Floyd's algorithm. So if your length of the loop is n, and if the distance is increasing by 1 in every iteration, then when slow is here, how much time it will take? How many iterations it will take? It will take big O of n at most, where n is the loop length. And say there are some more nodes extra here. Say there are m nodes here before it enters inside the loop, right? So what will be the time complexity? Slow 1 by 1 came here and then big O of n. So it will be big O of m plus big O of n, where m is this length and n is the length of the loop, right? So this is big O of m plus n. And what is big O of m plus n? It's the length of the linked list. It's almost the length of the linked list, right? So that is why the time complexity of this Floyd's algorithm is linear in terms of linked list length. Also, it does not require any extra space. It does not make any modifications to linked list node structure, does not make many modifications to linked list, and works in big O of n time. So that's the best solution available for detecting cycle in a linked list.